Hello, my name is Shir Peleg, and this is a talk about polynomial time PAT algorithms for a certain subclass of depth-4 arithmetic circuits via Edelstein-Kelly type theorem for quadratic polynomials. This is a joint work with Amir Shpilka. So let me quickly recall what an algebraic or arithmetic circuit is. So an arithmetic circuit is a directed acyclic graph with inner load labeled by arithmetic operation, such as product or sum, and the leaves are labeled with variables and field constants. Such a circuit computes a polynomial over the given field. The size of the circuit is the number of wires in the graph, and the depth of the circuit is the length of the longest path between the root and a leaf. For example, this is a sigma pi sigma circuit, a depth 3 arithmetic circuit, where the top layer is a sum gate. Then the second layer is a product gate, consists of product gates, and then another layer of sum gates. The polynomial identity testing question asks you to devise an efficient deterministic algorithm to determine whether the output of the circuit is the identically zero polynomial. So if phi is identically zero. There is an efficient probabilistic algorithm for this problem using the Schwarz-Zippel, the Miller-Lipton lemma. We can just pick a valuation point uniformly at random and plug it into the circuit. If the polynomial that is computed by the circuit is not the zero polynomial, then with high probability, the valuation on our random point will not be zero. De-randomizing this problem has application to arithmetic circuits lower bound, perfect matching in NC2, deterministic polynomial factoring, and many more. An interesting fact about the PAT problem is that solving it for small depth arithmetic circuit is essentially enough. A remarkable theorem by Agrawal and Vinay from 2008 states that constructing a polytime PAT algorithms for depth-4 arithmetic circuits implies a quasi-polynomial time PAT algorithm for general circuits. This result was later generalized by Gupta, Kamas, Kayal, and Saptarishi in 2016, where they proved that the same result holds for depth-3 arithmetic circuits or sigma pi sigma circuits over field with characteristics 0. So let's take a quick look at previous result regarding polynomial identity testing for small depth arithmetic circuits, namely for depth 3 arithmetic circuits. This is a line of work started with Dvir Shpilka, and then Kayal and Saraf, Saxena, Seshardi, and many more. I'm not following any specific work, but describing the main idea behind those algorithms. So let us consider a depth 3 arithmetic circuit where the top fan-in is bounded by 3. So the polynomial computed by the circuit, phi, can be represented in the following form. So there are 3 summons. Each of them is a product of polynomials. Those polynomials have total degree at most 1 because the bottom layer is only a sum gate. So the output of the polynomial, again, can be represented as 3 summons of product of polynomials of total degree at most 1, or affine polynomials. Now, if we assume that the output of the circuit is the 0 polynomial, then for every valuation point, our polynomial will output 0. Specifically, if we take 2 factors from 2 different product gates, so for example, L2j and L3j prime, and we look at the common 0 of them, this valuation point will vanish the third product and the second product. So it must be that the first product vanishes as well. So whenever we have a common 0 of L2j and L3j prime, the product of the polynomials in the first product gate also vanishes. And this is true for any polynomial from any 2 polynomials from 2 different product gates. Using Edelstein-Kelly theorem, which is a mathematical theorem that I will explain to further details later, you can deduce that the dimension of the affine polynomials involved in the circuit is bounded by a small constant. This essentially means that the circuit only relies on a constant number of variables. And then you can devise the PAT algorithm quite easily, because you can, in some sense, just brute force your way into a non-zero valuation. So this is the main idea behind depth-free PAT. Now let's try to extend this idea for depth-4 arithmetic circuits. So this is a depth-4 arithmetic circuit, or sigma pi circuit. And let us assume that the top fan-in, again, as before, is bounded by 3, but now we also assume that the bottom fan-in is bounded by 2. That means that such a circuit computes a polynomial of the form, again, we have 3 summands, each of them is a product, but if now we have that the inner polynomials have the total degree at most 2, where before, when we had depth 3, we had that the total degree was at most 1. Up until this work, there was no sub-exponential PAT algorithm for such circuits, but there were results for restricted submodels, and this problem has been studied quite a lot. So let's try to follow the same ideas that we described for the depth-3 circuit. So again, if the output of the polynomial of the circuit phi is the identically zero polynomial, then for every q2j and q3j prime, when we take a common zero of them, the first product must vanish at this point. So again, we have that the product of the first gate, the first product gate, is vanishing whenever 2 quadratics vanish. So we have a similar condition, but now instead of affine polynomials, we're working with polynomials of total degree at most 2. Can we say anything about the dimension of such a set of polynomials? So we hope that in order to do so, we should understand how it was done where the degree was at most 1. So let me explain, let me introduce Edelstein-Cayley theorem. Edelstein-Cayley theorem is a theorem in a discrete geometry that states the following. So assuming you have 3 sets of disjoint complex points, and you have the following property. Whenever you choose 2 points from different sets, and you draw the line that goes through them, this line intersects the set in the third set in some point. This is what we call an Edelstein-Cayley configuration. So if you have an Edelstein-Cayley configuration, then the theorem states that the dimension of the point is smaller or equal to 4. That means that the point lives in a complex space of dimension at most 4. There is an equivalent algebraic theorem for Edelstein-Cayley, which states the following. So if we have 3 sets of pairwise linearly independent linear forms, by that we mean homogeneous linear polynomials, and assume that they satisfy the polynomial Edelstein-Cayley condition, which is if we have we take Li from one set and Lj from another set, there exists a third linear form Lk in the third set such that whenever Li and Lj vanish, so does Lk. Then the dimension is bounded above by 5. The dimension of all the linear forms in the configuration is bounded above by 5. The only known result for this algebraic statement is using Edelstein-Cayley, the original geometric Edelstein-Cayley theorem. But recall that for the PAT, the condition for PAT for depth-3 arithmetic circuit, we had a product of linear forms that vanished whenever we had 2 linear forms vanish. So when we are working with polynomials of total degree 1, assuming that the product vanish, essentially says that there is a unique polynomial in the product that vanish when those 2 linear forms vanish. So that means that the product implies the uniqueness. And this is not true for higher degree polynomials. So from now on, we have 2 Edelstein-Cayley conditions, or polynomial Edelstein-Cayley condition. We have the product condition, where we have that a product of polynomial vanish whenever 2 polynomials vanish. And we have the unique condition. where there is a unique polynomial that vanishes whenever two polynomials vanish. So Beacon, Mitman, and Saxena, and later Gupta asked whether the same property holds for higher degree polynomials. Specifically, we have three sets of degree R polynomials that satisfy the product Edelstein-Kelly condition. That means that whenever we take two polynomials from two different sets, whenever they vanish together, then the product of the polynomials in the third set vanishes as well. And they ask, can we bound the algebraic rank of the polynomials in our sets? So as I explained earlier, when the degree is 1, this follows from Edelstein-Kelly theorem, where the product implies uniqueness, and then we can apply Edelstein-Kelly. When R equals 2, this is our result. So we proved a generalization of Edelstein-Kelly for degree 2 polynomials or quadratic polynomials. And when R is greater or equal than 3, which means that the polynomials are cubic or have higher degree, this is an open and very interesting problem. So let me formally present our main theorem. So we prove an Edelstein-Kelly equivalent for quadratic polynomials. So you have 3 sets of polynomials of total degree at most 2, and they satisfy the product polynomial Edelstein-Kelly condition. So whenever we take 2 quadratics from 2 different sets, whenever they vanish together, the product of the quadratics in the third set vanishes as well. Then the dimension of the span of the polynomials involved in the configuration is bounded above, but by a constant we denote lambda 2. So let me note 2 small things. This result is a little stronger from the conjecture of BMS and Gupta. This is because we bound the dimension of the linear span of the polynomials and not the algebraic rank, which is indeed stronger. The second thing I want to mention is that our upper bound is constant, but a rather large constant that we did not write explicitly. You saw that in the case of linear polynomials, or where the degree was 1, we have an upper bound of very small constant, 5. And those constants were tight. We do not believe that our result is tight. And indeed, it is very interesting to understand the correct constant that should be written here. As I mentioned before, an immediate corollary of this result is the polynomial identity testing algorithm for sigma pi circuits, where the top fan-in is bounded by 3 and the bottom fan-in is bounded by 2. And furthermore, there is an explicit heating set for such circuits. So before I give the overview of our proof, let me state some previous interesting results regarding those theorems. So Edelstein-Kelly theorem is a colored version of Sylvester-Galai theorem. Sylvester-Galai theorem states that if you have a configuration, one set of points, such that whenever you take 2 points from the set and draw the line that goes through them, this line intersects the set in a third point. And then the dimension of the point is bounded above. So in Edelstein-Kelly, we have 3 sets, and in Sylvester-Galai, we have 1 set. So this is why we call Edelstein-Kelly a colored version of Sylvester-Galai. Note that we cannot prove Edelstein-Kelly using Sylvester-Galai in a black box manner or the other way around. So they are in some sense incomparable. As I mentioned before, Edelstein-Kelly theorem was studied in the connection to PAT algorithms for sigma pi sigma circuits. Barak, Dvir, Vigderson, and Yehudayev, and later Dvir, Saraf, and Vigderson prove a robust or fractional version of Sylvester-Galai theorem. In this result, they prove that if you have a set of points such that for every point there is a delta fraction of the other points, such that the line that goes through this point intersects the set in a third point. So then they proved that if you have such a fractional or robust Sylvester-Galai configuration, the dimension of the points is at most some function of 1 over delta. They use the result to construct locally correctable code, and we use the result to extend Edelstein-Kelly and Sylvester-Galai to a higher degree polynomials. In 2019, Shpilka and later Shpilka and myself generalized Sylvester-Galai theorem for quadratic polynomial. The first work gave a bound where we had a unique Sylvester-Galai condition, and the second work generalized it to the product condition. Shpilka 2019 also generalized Edelstein-Kelly to quadratic polynomials, but this is using the unique Edelstein-Kelly configuration assumption. So his result did not yield the desired PAT algorithm. Now let me give a quick overview of our proof. An important tool of our proof is the following structure theorem given in the work of Shpilka and myself in 2020. This theorem categorizes the different cases in which a product of quadratic polynomials vanish whenever two other quadratic polynomials vanish together. So we have a set of quadratics and two other quadratics, A and B, such that whenever A and B vanish, the product of the QKs vanish as well. Then one of the following cases must hold. Either A and B span one of the polynomial QK, so there is one of the polynomials in the product is in the linear span of A and B, or A and B span a reducible quadratic polynomials. That means that there are two linear forms, L1 and L2, such that A and B span the product L1 times L2, or that both A and B lie in the ideal generated by two linear forms. By that we mean that in some sense they have low complexity because they can be represented as a sum of two reducible quadratics. This is not the general case of quadratic polynomials. So these are the only three cases that can be when we have that the product of quadratic polynomial vanishes whenever two quadratic vanish together. We proved that all three cases are indeed different and all of them are possible. So now let me give a quick overview of how we proved Edelstein-Kelly for quadratic polynomial using the structured theorem. So as I said, our goal is to prove the Edelstein-Kelly for quadratic polynomials. And our main idea is to reduce the problem to the original Edelstein-Kelly problem or a fractional version of it. So what the structured theorem essentially gives us is the following graph that I draw here. So we have a tripartite graph. Each side of the graph represents one of the sets. And whenever we take two polynomials from two different sets, the product of the polynomials in the third set vanish. They mean that they satisfy the condition of the structured theorem. Thus, they either satisfy case 1, case 2, or case 3. So if they satisfy case 1, we draw a blue edge between them. If they satisfy case 2, we draw a red edge between them. And if they satisfy case 3, we draw a green edge between them. So we have a complete tripartite graph. I did not draw the edges between T1 and T3 just for convenience, and I did not draw all the edges. But now we study how this graph looks. So what are the colors of the edges? And we want to use each case to deduce a reduction to the original Edelstein-Kelly theorem, either for the coefficient vectors of the quadratic. Either we claim that they satisfy Edelstein-Kelly or a robust version of it, or that we prove that the linear forms that our polynomials rely on satisfy Edelstein-Kelly property condition. And this is done, as I mentioned, using case analysis and the structure theorem. So let's take the first step and assume that all the edges in the graphs are blue. That means that every two polynomials from different sets satisfy case one of the structure theorem. Then we can just apply Edelstein-Kelly theorem for the coefficient vectors of our quadratics and get that the dimension of the set is bounded by 5. So this is the easiest case. Now let's assume something a little bit looser. So instead of having all the edges in the graph blue, we say that we assume that every polynomial have 1% of the edges that go through him blue. That means that for every polynomial qi in one set, it satisfies item 1 of the structure theorem with 1% of the other polynomials in the other sets. Thus, we claim that the dimension that we can use the robust version of Edelstein-Kelly or a fractional version to bound the dimension of the polynomials in the set. And we did need to prove such a robust version of Edelstein-Kelly theorem. The other case we considered is that every node has either a constant fraction of blue edges or a constant fraction of green edges. So that means that every polynomial qi satisfied either case 1 or case 3 with 1% of the other polynomials. And recall that by case 3, we mean that it lies in an ideal generated by two linear forms, or what I called the low complexity case. So it is a polynomial of low complexity. In this case, we iteratively collect the linear forms that involved in the polynomial of small rank. So the polynomials that satisfy case 3 of the structure theorem a lot. And we claim that the polynomials that we did not cover in this manner satisfy the robust Edelstein-Kelly condition by themselves. Thus, the last case we have to consider is that there is at least one polynomial in the set that satisfy case 2 of the structure theorem with almost all the other polynomials. So it has a lot of, most of its edges are red, almost all of its edges. And recall that by case 2, we mean that they together span a reducible quadratic. This case is handled separately, and it is the most complex case, and I will not go into details into the proof. So let me conclude the talk by describing direction for future research. So the main goal of this research is to construct PIT algorithms for depth 4 arithmetic circuits. In order to do so, we need to allow higher bottom fan-in of the circuit and higher top fan-in of the circuit. For the bottom fan-in, we needed to have similar results for higher degree polynomials. So the bottom fan-in corresponds to the degree of the polynomial. For the top fan-in, this allows more sets or more colors in the Edelstein-Kelly theorem. So any progress in any of those directions should be very interesting. As I mentioned, we relied heavily on the robust version of Sylvester Galai and Edelstein-Kelly for our result. We needed a robust version for linear forms in order to prove a quadratic version. So we believe that a similar result should be needed to go from quadratic to cubics. So we might want to prove a robust version for quadratic polynomials. We also might wonder if the same result holds for positive characteristics. And the last question I want to talk about is proving tighter bounds. As I mentioned before, our upper bound is constant, but a rather large constant. And for the linear case, the problem is completely solved. There is a matching upper and lower bound. So can we understand this problem in the same manner? Can we give a lower bound that goes together with the upper bound? We don't believe that our upper bound is the correct one. So thank you very much for listening, and I hope you enjoyed the talk.